I'm going to do this problem twice. There's two main ways that I'm going to teach you to solve exponential equations, and the first method only works when the numbers are fairly simple, easy numbers, when kind of a coincidence happens, and the second method works every single time. So let's do the simple method first. The simple method is based on trying to get the bases on each side the same. So the base here is 2. So we try to write 16 as a power of 2, and if that's possible, we can do this first method. It is possible because 4 2's multiplied together is 16. Now once you have an equation where the bases are equal on both sides, and you just have that base to a power on the left and that same base to a different power on the right, then there is a property that says in that case the two exponents have to be equal. So once we get those powers the same, we can get rid of them and just equate the exponents. Adding 1 to both sides, we get x equals 5. This can be checked in the original equation by taking the original equation and replacing the x with what we think x equals. 2 to the 5 minus 1 power is 2 to the 4th power, and this checks. 2 to the 4th is 16. That only works, this method only works when we can make the bases on both sides alike. If this was a 15 instead of a 16, no dice. So what's a method that works basically always? And that is to do what I showed you in the last section, even though it didn't really belong in the last section. So what you can do is take the logarithm of both sides. I'm going to take the log base 10 of both sides because it's on my calculator. I have two things that are equal. I can take the logarithm of both sides, and those logarithms should be equal. Now this can come down in front and be multiplied. That was one of our properties. And then we can divide both sides by not anything with a b, but the log base 10 of 2. And we're getting x minus 1 equals the log base 10 of 16 divided by the log base 10 of 2. And we could add 1 to both sides and get x equals the log base 10 of 16 divided by the log base 10 of 2 plus 1. So this seems like it's a lot of extra work. This seems to me to be easier, and if you can get a like base, this is easier. That's one of the reasons we teach it. But over here, I'd have to use a calculator to find this and a calculator to find this, and that's kind of making me a little bit upset because you would think that there would be something else that we could do. And there are some things we could do, but one of them is we could have taken the log base 2 of both sides. And that means all these logarithms all the way through would have been base 2 logarithms. And then at this point, we could have said, well, what's the power you raise 2 to get 16? It's 4. What's the power you raise 2 to get 2? It's 1. And look what x is going to equal. X is going to equal 5. Let's try this again on a slightly different problem. So now we could take the logarithm of both sides. We can't write this as 2 to a power because it's not a power of 2. And we can take the exponent down in front and multiply it by the logarithm. It's one of our properties. And we can divide the logarithm base 10 of 5 divided by the logarithm base 10 of 2 on the calculator, and that will give us the answer, the solution to this equation. Pretty neat. How can we solve this equation? Well, what do we know? We know that when we have a sum of two logarithms, we could write it as the logarithm of one thing, the product. So I'll put it all in here. The logarithm of a product of two things is the sum of the individual logarithms. And now that's the logarithm. Distributing this through would have x squared plus 9x. But logarithm without a base is an implied base of 10. So let's turn this into an exponential equation just for the heck of it and see what we can do. The base 10 to the exponent. Remember, the logarithm is a power, so this is the power. And this is the result. Subtracting 10 from both sides, I have a quadratic equation. I could drag out the quadratic formula, but I feel like this may be factors. I'm getting x equals negative 10 from this, or x equals 1 from this. These must be checked, and when I try to put in a negative 10, for instance here, I'm getting the logarithm of a negative number. That's impossible. Let's see why. What's the power you raise 10 to get negative 10? And the answer is, anytime you raise a positive number to any power in the known real world, you get negative. You can't get a negative answer. If this exponent is negative 1 trillion, you'll just get a number close to 0 but still positive. If it's 1 trillion, you'll get a huge positive number. You can never have a positive base to a real power that gives you a negative number. It's impossible. So this is just flat out impossible. It doesn't check. This checks very nicely, so it's the solution to our equation.